Yes, ma'am.
So chapter 4 is on two topological models, and you know models means representation, some kind of representations of the actual system. So models could be mathematical models like differential equations or integral differential equations or transfer function or state space model, and a different type of representation could be a visual representation, a pictorial representation, and those representations are called topological models. Now, for linear systems, two topological models are of interest. One is block diagram, of which you are quite familiar, with which you are quite familiar, and the second one is signal flow graph. So first we'll discuss block diagram algebra, and before that we'll discuss what is actually block diagram representation of a system. And since you know all these things, so I'll go a little bit fast. If you find any difficulty, please feel free to ask your queries or doubts. So this is, we can consider this to be an open loop configuration of the system where RS is the input and CS is the output. RS, CS are represented in the transformed domain, and RS is input to this system. This is basically the system, and CS is the output generated by the system. So GS, the transfer function or open loop transfer function of the system, could be written as CS by RS, and we see this is nothing but GS. So along with this, just like this, when we'll be considering a family of interconnected elements representing a system, then each element can be represented with the help of such a block and the associated transfer function describing the dynamics of that particular element. And if the elements are non-loading elements, then only we can represent the system with the help of block diagram, right? So the elements will be shown as cascaded blocks in proper sequence. And finally, we'll have to identify the output generated by the system and input given to the system, and accordingly we find out the function of. Now, along this with associated transforms described by is, often we need summer or subtractor. Summer, or rather summers and subtractors. So this is the symbol used for representing a summer. Here you see two signals are given as input, and at this point we are getting a signal which is summation of this signal as well as signal. That's why this is a summer. And in this case again we are getting two signals, and at this point getting the difference of these two signals. So this is called a subtractor. And also this representation is of importance. This point is called takeoff point. Why it's called a takeoff point? From this particular point we are taking off some signal. Suppose this path represents the flow of a signal. Actually in the block diagram, in the direction of arrow, the direction of arrow actually indicates unique flow of signal, the direction of flow of signal, right? So we can assume that the signal is flowing, a particular signal is flowing, and from this particular point we are taking off the signal for some purpose. So these are the common what should I say, common features that will see while developing a block diagram. A block diagram of a closed loop system. You know this. RS is the reference input. CS is the output signal or controlled output. That's why we use this C, controlled output. BS is the feedback signal. ES is the actuating signal or error signal. And let me show you the block diagram. So this is the block diagram of a closed loop system. This is the closed loop configuration. So GS is the forward path element, whereas HS is the transfer function of the feedback path element. This is the feedback path, right? Now ES is the actuating signal or error signal, as ES is RS minus BS, where BS is the feedback signal, CS is the controlled output, and GS is the forward path gain, HS is the feedback path gain. And from this diagram, it's clear that BS, this particular signal, is equal to HS into CS, and CS is equal to GS into ES, right? And this error or actuating signal is RS minus BS. And this is the takeoff point. So we can develop the transfer function of the closed loop system. So with this notation, we can write, as I said, GS is equal to CS by ES, or CS is equal to GS into ES. HS, transfer function of the feedback element that we have discussed. And so GS into HS will be BS into ES. This is called GS into HS is called the loop transfer function. I guess you know all these things, right?
Yes, ma'am.
So CS is equal to GS into ES, whereas ES is equal to RS minus BS. So this can be written as RS minus HS into CS. So CS, we know that GS into RS minus GS, HS, CS. This equation we can obtain from the previous equations, right? Now after side transposition, we'll get, in the left hand side, we'll get CS into, within bracket, 1 plus GS, HS. So CS by RS, the closed loop transfer function of the system, will be equal to GS by 1 plus GS, HS. Now that is the transfer function for single input, single output system. There is a single input to the system and the system is generating a single output. So CISO system. Now if we consider multiple input, multiple output system, right? Now how to find out the response of the system? Since we are discussing a linear system, hence what can be done? Let me show you the diagram first. Please correct this diagram. This part is all right. This is the first summer. RS is the one input, and this is the summer. This is the feedback signal. It's basically a subtractor. So this is the actuating signal which is passing through this block, or which is basically input to this block G1S, and the output of this block, output generated by this block, is given to another summer. This negative sign will not be over here. Okay, so here you put a plus sign, and also here you put a plus sign, and this is the second input, US. So US over here in the summer, here we should put a positive sign, and also here we should put a positive sign. This sign is not relevant because at this point we don't have any input. You get my point?
Yes, ma'am.
So please correct the diagram, redraw the diagram properly. Done? Done?
Yes, ma'am.
Okay. So in this case, if we want to find out the output generated by the overall system when both the inputs are present, the process will be, first we'll assume that one single input is present, the other one is zero, right? So let's assume first that only this input has been applied to the system and this US is equal to 0. So for RS only, we'll find out the output generated by the overall system and let's call it C1S. Similarly, after finding out C1S, next we'll assume that RS is equal to 0 and US has been applied to the system. And we'll try to find out the output generated by the system, and let us assume that the output is C2S. Then from the superposition theorem we can say that when both the inputs will be present, will be applied on the system, that is RS is present and US is present, then the output of the system CS will be equal to C1S plus C2S, right? So in this manner we can find out the overall response of the system. Now, as I said, let's assume that RS is present and US is 0, and let's call CRS to be the output due to RS acting alone. Now since US is 0, hence this summer will not be required anymore, right? So the signal generated by this particular block will be simply input to this block. Okay, so the summer will not be required, so we can join the line, and it's clear, it's apparent that the output from this block will be the input to this block, and the transfer function CRS by RS will be equal to, this is the forward path, this is the forward path, this is CRS now, and this is RS input. So the transfer function will be given as G1 into G2 whole divided by 1 plus G1 G2 into HS, right? So CRS, from this block diagram, CRS could be obtained as G1S into G2S by 1 plus G1 into G2 into H into RS, right? Now next, let's assume that RS is 0 and US is present, right? Now RS is 0, but we cannot simply ignore this summer in this case. Why? Because of the presence of this minus sign. What will be the signal over here? The signal will be HS into CS, and the significance of this minus sign is that the signal HS into CS, or rather CUS is getting multiplied by -1. So the signal at this point will be negative. So if I consider that the signal at this point is simply positive, then I can carry forward this minus sign at this point. This is plus, and the minus sign will be, I can carry forward the minus sign over here. So ultimately this signal CSHS will be negative. Do you get my point?
Yes, ma'am.
Okay, so if we do so, then the configuration will be simply a negative feedback configuration. Like this. Clear? So, okay. So since now US is present and the output is CUS, you see this block is actually connecting the output to the input. So in this case, this is the forward path. This is actually the forward path. In the previous case, that was the forward path, as this path was connecting the output to the input directly. Now in contrast, in the second case, you see the output is being connected to the input signal through this block only. So this is the forward path, and all the other elements will be in the feedback path, and it will be a typical negative feedback system. So if I simplify this block diagram, when US is present, the block diagram will look like this. There is a forward path gain G2S, and the feedback path gain will be G1 and HS in a cascaded mode. So CUS by US now will be G2S by 1 plus G1 into G2 into HS. So that is CUS by US. So CUS will be G2 by 1 plus G1 G2 HS into US. So now we can combine these two outputs, CR and CU, to get the actual output of the system when both the inputs are present. Have you understood this?
Yes, ma'am.
So we can generalize this concept. So this is the output. So we can generalize this concept. Let's assume that this is our system and there are R inputs and M number of outputs. R inputs are R1, R2, RR, and M number of outputs are C1, C2, CM, as you can see, right? So in this case, if we want to find out the first output, because of the presence of all these inputs, so what we'll have to do? First of all, we'll have to assume that R2 to RR, all these inputs are 0, and we'll have to find out C1S when only R1 is present. Then we'll have to find out C1S when only R2 is present. Then we'll have to find out C1S when only RR is present. And then If we add all the inputs, then we'll get this. Actually, for R1 we'll get, say, C11 is, for R2 we'll get C12s, and for RR, say, suppose we will get C1RS. So if we join all these inputs, we'll get C1S because of all these inputs. Similarly, for C2S, we'll have to follow the same procedure. Do you understand this? Have you understood this process?
Yes, ma'am.
So you say here it's written that C1S is basically summation of, this is the transfer function, this is the transfer function G1J. G1J means the transfer function where the output is the first output, and because of the jth input, this transfer function we are obtaining when the input is the jth input and the output is the first output, right? Multiplied by rj's because of the jth input. So this should be multiplied by multiplied with rj's like this. Like this. Clear? So this will have to perform for C2S, C3S, CMS, right? So now we can generalize, the expression is not written over here. We can generalize this to be CIS will be equal to summation of J varying from 1 to R, Gij, where I is the ith output and J is the jth input into Rj's. So J will be varying from 1 to R and I will vary from 1 to N because N number of outputs are there, and we'll have to obtain the sum. Clear?
Yeah, ma'am.
Now, so far what we have seen block diagrams, block diagram representation of the systems, where the systems are pretty simple. And consequently, the block diagrams representing those simple systems are also very simple. And often the block diagrams are a single loop block diagram. There is one single loop, right? So to find out transfer function is pretty simple, very easy. Just we know that particular formula, that Ts will be equal to Gs by 1 plus Gs Hs, where Gs is the overall forward path gain and Hs is the overall feedback path gain. Now for complicated system, complex system, the transfer function, sorry, the block diagram also comes out to be a complicated one having multiple loops, right? So that's why just having a mere inspection of the block diagram, finding out the transfer function is not so easy. Not so easy. So that's why we'll learn a few rules. With the help of those rules, we can reduce the complex block diagram having say several loops into a simple single loop block diagram where we can apply that particular formula, that is the transfer function, overall transfer function is given by the forward path gain by whole divided by 1 plus forward path gain multiplied by feedback path gain. That means we can eliminate the loop and thereby we can find out the transfer function of the system. Okay, so this is known as, this technique is known as block diagram reduction technique. That means you are eliminating multiple loops, and finally you are representing the system with the help of a single loop block diagram, and therefrom you are finding out the transfer function of the system. So this technique is known as block diagram reduction technique. See, the title is the subsection is block diagram reduction. So for that, just we'll learn a few rules, very simple rules. So generally we apply these rules for finding out or for reducing the block diagram into a simple single loop one. Now the first is combining blocks in cascade. So when we'll try to reduce the block diagram, right, one thing we should keep in mind that signal value at a point, at a particular point of the block diagram, of the topology, will always remain same. You get my point? The signal value at a particular point of the topological model of the system cannot change. Okay, so that means in a straightforward manner, input to the system and output from the system should always be same. Even if we reduce the block diagram, the input to the system and the output from the system will always remain same, right? Otherwise the block diagram will change. Transfer function will change. Okay, so here you see we do have two blocks. One is G1 and other one is G2, and signal X1 has been applied on this particular block G1, and naturally at this point the signal value, at this particular point the signal value will be X1 into G1, right? And this signal is basically input to this block, and hence the output, this is the output signal from this configuration. So the output signal will be X1 into G1, G2. Now what we want to do, we want to combine the blocks in cascade, right? So if we just multiply the transfer function of these two cascaded blocks, and if we represent two blocks with the help of a single block having the transfer function, or you can say gain, like G1, G2, then if we give X1 as input to this particular block, the output will be X1, G1, G2. So the input to this configuration and the output from this configuration, you compare with this, are same. Hence, this configuration can be represented with this configuration as well. So we can combine the blocks. Here I have shown two blocks. It could be 3 blocks, 4 blocks, right? So blocks can be combined where the blocks are placed in cascaded manner. Now in this diagram, what is our objective? Our objective is to move a summing point or a summer after a block. So this is the initial or original configuration. Here you see there is a summer, right? And two input signals, one is X1, the other one is X2, right? So at the output of the summer, just I'm considering it to be a summer. It could be a subtractor as well. So it has been shown with the help of this plus minus sign. So the signal at the output of the summer is X1 plus minus X2. Now the signal is passing through a block having a gain G, and hence the output, we are getting a signal which is G X1 plus minus X2. Now our objective is to move this block ahead of this summer, or in other words, we want to move this summer after the block. So let's just put the summer, don't look at the signals right now, just put the summer over here, right? So since we have taken this block ahead of the summer, so naturally here will place the block, right? So x1, this signal will be an input to that particular block, okay, because x2 is the input to the summer. So just if we move this block in this position, can you visualize? Can you visualize? Hello? Can you follow this? Can you visualize? No response. So if we place the block over here, then x1 will be input to the block. So x1 is indeed input to this block G, and after that we have put the summer. So the one input to the summer is x1G. x1G. Now if we directly apply the second signal x2 to the summer, then at this point we'll get a signal which is x1G plus minus x2, but that is not the signal being generated by this system. The signal is gx1 plus minus x2. So if we want to move this block ahead of this summer, in this path, in the feedback path, we'll have to place a block in addition. Additionally, we'll have to introduce a block having a gain G. If we do so, then you see this is the input to the block x2. So this is the signal at this point x2G. So at the output of the summer, we'll get our Desert signal, which is G into x1 plus x2. Have you understood this?
Yes, ma'am.
Now next, in the original configuration, you see, first we are coming across a block, and then we have then a summer has been placed, right? Now we want to move the summer ahead of the block. Here we have moved the summing point after the block. Here we want to move this summer ahead of the block. Now let's first analyze the original configuration. So the signal input signals to the summer are x1G, and this is x2. So the output signal is x1G plus minus x2. So if we move the summer ahead of the block, so x1, this first signal will be input to the summer, right? And the output will be at this point, the output is x1, the first signal. Now if you directly fit the second signal x2 to the summer, then at this point the signal will be x1 plus minus x2, and then we'll have to put the block having a gain G, right? So the output signal will be x1 plus minus x2 whole multiplied by G. So that is not the Desert signal. The Desert signal is x1G plus minus x2. So again, in the feedback path, we'll have to introduce an additional block. Now the gain of the block should be 1 by G. So the signal at this point will be x2 by G. The signal at the output of the summer will be x1 plus minus x2 by G. x2 by G, and when the signal will pass through a block having a gain G, the output will be the Desert one, that is x1G plus minus x2. Clear?
Yes, ma'am.
Next, moving a takeoff point after a block. In the original configuration, you see the takeoff point. This is the takeoff point. The takeoff point is ahead of this, placed ahead of this block. So this is the signal x1. So actually we are extracting, we intend to extract the signal, we intend to take this signal x1 off from this particular point, and this x1 is the signal input to this block and the output is x1g, right? So if we place this block in this position, then the output signal will be x1g, and that is not the signal that we want to extract, right? So that's why what we'll have to do, if we just move this block in this position, this is the signal x1g, but we need the signal x1, so the signal has to be passed through a block having a gain 1 by g, and then only we can use the signal x1 for our requirement. Similarly, moving a takeoff point ahead of the block. Here the takeoff point is placed after the block. We want to move it at this particular point, right? So if we directly move the takeoff point at this point, then the signal that we'll get is x1, which is not the desired signal. The desired signal that we want to take off is x1g, right? So if we just move this point to this point, then in this path we'll have to introduce a block having a gain g, so that the signal that we are wanting, it becomes x1g. And the last rule that is known to you, eliminating a feedback loop, that is the closed loop configuration, single loop closed loop configuration, and the transfer function x2 is now the output and x1 is the input. So the transfer function will be given by g by 1 plus minus gh. Have you understood the rules?
Yes, ma'am.
So now we'll discuss one example where from the first principle we'll first develop the block diagram of the overall system. Starting from the first principle, we'll develop the block diagram, we'll write down the differential equation describing the dynamics of the system, and therefrom we'll develop the block diagram. After that, we'll try to reduce, if we find that the block diagram is a complicated one having a number of loops, right, then we'll try to reduce the block diagram with the help of the rules that we have discussed so far, and finally we'll try to find out the overall transfer function of the system. So the example is of a liquid level system. So this is the system. As you can see, two tanks are connected via a pipe, right? H1 is the head of the liquid in the first tank, and H2 is the head of the liquid in the second tank, right? And here Q should be written, which is the inflow rate Q. Q1 is the outflow rate from the first tank, and Q2 is the outflow rate and the actual output of the system. So Q2 is the output of the system, and Q, the inflow rate, is the input to the system, right? Now here it's not possible to find out, to consider one single tank and find out its transfer function and then just changing the parameters, represent the second tank with the same transfer function and put those blocks in cascaded manner. Why it's not possible? Because you see the second tank is loading the first one. The liquid can flow from this particular tank to this particular tank like current flow. That means this tank is loading this particular tank, right? So that's why we'll have to consider this system, the overall system, as an integrated system, and we'll have to find out the transfer function considering two tanks, considering this two tank system. Now, if we assume that you have studied liquid level system, right? In your system theory class, you have studied, I guess you have studied liquid level system. Hello? Okay. So Q is the inflow rate. Now let's assume that there is a small change in the inflow rate. So this small change is denoted by delta Q. So if the inflow rate changes by a small amount, which is delta Q, that will result in a change in the head of the liquid in tank 1 as well as the head of the liquid in tank 2. Okay. So let's assume that the change in head of liquids in both the tanks are denoted by delta H1 and delta H2 respectively. And similarly, if we change the inflow rate Q by delta Q amount, obviously this Q1 will change by an amount, let's assume, which is given by delta Q1, and Q2, the outflow rate, will also change by an amount delta Q2. So if delta Q, so let delta Q be a small deviation in the inflow rate Q. This results in delta H1, small deviation of the head of the tank 1 from its steady state value, delta H2, small deviation of the head of the liquid in tank 2 from its steady state value, delta Q1, small deviation of the outflow rate of tank 1 from its steady state value, and delta Q2, small deviation of the outflow rate of tank 2 from its steady state value. Now the flow balance equation here, we're assuming laminar flow, obviously laminar flow, because delta Q is a small change in the inflow rate. Okay. So if you assume laminar flow, then you see the flow balance equation will be input delta Q will be change in the head of the liquid in this tank, and change, some combination of this change in head of the liquid and change in the outflow rate. So delta Q will be simply delta Q1 plus, this tank can be characterized like a capacitor because this tank can store liquid, right? So it's basically a storage element, hence we can apply our analogy and we can represent the tank with the help of a storage capacitance. Let me show somewhere over here. Yes, it's written over here. A tank having a liquid capacitance C1 is supplying liquid through a pipe of resistance R1. R1 is like a cable having a resistance R1 through which current can pass. Similarly, the second tank will have a liquid capacitance C2, and the second pipe, the output pipe, will have a resistance R2. So now we can, from the first principle, we can write down the differential equations describing differential as well as algebraic equations describing the dynamic behavior of the system. The first one is delta Q change in inflow rate will be equal to delta Q1 change in the outflow rate from tank 1 plus change in head, that is C1 into ddt of delta H1, right? Similarly, for tank 2, the flow balance equation will be delta Q1, that is will be equal to delta Q2 changing the outflow rate from tank 2 plus changing heads, that means storage, that is C2 into ddt of delta H2. Now H1 is the head, or delta H1 is the change in the head in tank 1, and delta H2 is the change in head in tank 2, right? And tank 1 and tank 2 are connected via pipe having a resistance R1. So delta Q1 flow from tank 1 to tank 2, delta Q1 will be equal to delta H1 minus delta H2 divided by the resistance of the pipe, just like a wear, acting like a wear, current carrying wear, right? So divided by R1, and the change in the outflow rate delta Q2 will be simply delta H2 by R2. Have you understood these 4 basic equations?
Yeah, ma'am.
So these 2 are the 2 differential equations. These 2 are simple algebraic equations. Now our objective is to develop the block diagram representing this particular system. Hence, we'll have to take Laplace transform of all these equations. So if you take Laplace transform the first equation, then, and just you see, so that we can very easily develop the block diagram. Hence, if we just take this in the left hand side, we'll get delta Q minus delta Q1, which represents that we'll be requiring a sum. Okay, so delta Qs minus delta Q1s is equal to SC1 delta H1s, SC1 delta H1s. So if you want to obtain this signal delta H1s, then the output from the summer which is actually resulting in a signal which is delta Qs minus delta Q1s, that signal will have to pass through a block having a gain 1 by SC1, and at the output of that block we'll get this particular signal delta H1s. Do you agree? Do you agree?
Okay, ma'am.
Similarly, the second equation, delta Q1s minus delta Q2s. So it's obvious that we'll be requiring another summer, will be equal to SC2 delta H2s, or delta Q1s minus delta Q2s. If that signal is passed through a block having a gain 1 by SC2, then the output of the block will get the signal delta H2s, and these 2 are very simple. So delta Q1 is delta H1 minus delta H2 divided by delta H1s minus delta H2s divided by R1, right? So if you want to obtain the signal delta Q1s, again we'll be requiring a summer whose inputs will be, or subtractor rather, whose inputs are delta H1 and delta H2, and if that signal is passed through a block having a gain 1 by R1, then we'll get this signal. And simply delta H2, if that signal is passed through a block having a gain 1 by R2, then we'll get a signal delta Q2s. Right? Now, first what we will do, we'll first develop the block diagram representing each signal. Then we'll combine those parts of the block diagram. So otherwise, it will be difficult for us to develop the block diagram of the overall system in a single go. So let's first develop the block diagram representing this equation. So as I said, we'll be requiring this signal, this delta Q1S should be written over here. Otherwise it's quite apparent. It should be over here. The feedback signal is delta Q1S. So delta QS, and the second input to the subtractor is delta Q1S. So this is the signal, that is delta QS minus delta Q1S, and that is being passed through a block having a gain 1 by SC1. Hence we are getting a signal delta H1S. Do I have to show the equations again?
No, ma'am, it's okay.
Now the second one, delta Q1 minus delta Q2. So this is delta Q1 minus delta Q2 being passed through a block having a gain 1 by SC2. So the output signal is delta H2S. The third one was delta Q1S is equal to delta H1S minus delta H2S. The signal is being passed through a block having a gain 1 by R1, and the signal is delta Q1S. And this is a very simple one, delta H2S passing through a block having a gain 1 by R2, hence the value is delta Q2S. Now we'll try to combine these equations. How to combine? You see, here we are getting a signal which is delta H1S, and this is the part of the block diagram where the basic input to this part of the block diagram is delta H1S. So now we can combine this one to this one, right? So we can just put a summer over here where the input signal will be delta H1S, and we know that the second input has to be delta H2S. Then we can put a block which is having a gain 1 by R1. You get my point? So this is the part. So we have combined this one and this one. So delta QS minus delta Q1S passing through this block, we are getting delta H1S. So we know that from somewhere we'll get this feedback signal delta H2S, and the resulting signal will be passed through a block which is 1 by R1, and the output is delta Q1S. And in this part, we know that the feedback signal should be delta Q1S. So this is our delta Q1S. So this is the desired takeoff point. So we'll take off this particular signal and we'll feed back this signal to this particular sample. Clear?
Yeah, ma'am.
Okay. Now you see here we are getting a signal delta Q1S. So now you see, look at this part of the block diagram where yes, delta Q1S is the input signal, right? So we can put a summer over here where delta Q1S will be one input, and the second input we know delta Q2S will get that signal from some point, and after the summer we can put this block and we'll get delta H2. Okay, now we can take off delta H2 and we can draw a feedback path and we can feed back that particular signal to this summer. So delta H1 is 1 by R1. This part we have already developed. Now delta Q1S is applied to a summer. Delta QS, we don't know this part. We have not discussed this part yet. So now this is being passed through a block 1 by SC2 and the signal is H2S. Some T1 is written over here, takeoff point 1. This is T2, takeoff point 2. So we are taking off this particular signal and we are feeding back. So here we go, and at this point we are getting the signal delta H1S minus delta H2S. So here we are getting the signal delta H2S. So we are only left with this part. We have combined this one, and then this one. So you're left with this one. So now delta H2 will be passed through a block. We can combine this. We can uh, put this block over here having a gain 1 by R2, and we'll get the output signal, that is delta Q2S. Now we'll be requiring this signal for feedback purpose, isn't it? Delta Q2S. So this output signal will be fed back to this summer. So this is the overall transfer function, the complete transfer function of the turbo interconnected tank system. Clear? Have you understood how we have developed the complete block diagram representing the overall system? Have you understood?
Yes, ma'am.
Okay. Now our objective is to find out the transfer function of the system. Now you see, the problem is, just look at this particular loop. We can say there are 3 loops. Okay. Now first, if we consider this particular loop, we cannot eliminate this particular loop. Why? Because one takeoff point is present over here, right? So that's why in a straightforward manner we cannot eliminate this particular loop. We cannot eliminate this particular loop as well because of the presence of this sum. Similarly, this particular loop cannot be eliminated because a summer is present over here. So we'll have to go for block diagram reduction technique to obtain the transfer function of the system. So please note, in this diagram some corrections have to be done. So what we'll do first, we'll just move this takeoff point after this block. Please note, we'll move this takeoff point after this block. So if the takeoff point is this one, then the signal, obviously the signal that we are taking off, that is delta H2S. Now if we move this after this block, then the signal will be delta H2S by R2. So that is not the signal that we need for feedback purpose. We need delta H2S. Hence, if we want to move this takeoff point after this block, we'll have to introduce a block in this feedback path having a gain R2. Am I clear?
Yeah, ma'am.
Now, this diagram is incorrect. Now, since we have introduced this block over here, R2, so this feedback path will start from this point only. So this is incorrect. এই পাথটা থাকবে না, এটা এখান থেকে সিগন্যালটা আমরা এখান থেকে নিচ্ছি। Okay, if you want, you can draw this part of the block diagram যাতে পরে কনফিউশন না হয়, মানে ম্যাটেরিয়ালটা দেখার পরে কনফিউশন না হয়। এই পার্টটা please draw this part correctly. None. None.
Yes, ma'am.
Okay, ma'am. Done.
Okay. So if we move this takeoff point after this block, then you see there's a simple single feedback loop. So now we can eliminate this feedback path, right? So please check whether after elimination this one will be. Now in this diagram you see this is the takeoff point, and this has been correctly shown. This is the modified takeoff point, and the signal is same delta H2S as it's passing, as the signal delta Q2 is passing through this block having a gain R2. So the forward path gain is 1 by SC2 into 1 by R1, that is 1 by C1 R1, or sorry, 1 by SC2 R2, sorry, 1 by SC2 R2, that is the forward path gain, and this is the unity feedback one. So if we eliminate this, then this block representing this loop will have a transfer function which is G by 1 plus GH, and it will be 1 by R2C2S plus 1. So in the next step, again you see we cannot eliminate this loop or we cannot eliminate this loop. So what we'll do now, we'll just move this takeoff point after this block. So now the takeoff point will be this point, and even if you forget the rule, just keep in mind that the signal value should not change. So if I move this to this point, this takeoff point to this point, we'll have to introduce a block in this feedback loop having an appropriate gain, and the gain will be again 1 by this one, so the gain is R2C2S plus 1. So now we are in a position to eliminate this loop. Eliminate this loop. Please check whether the transfer functions of the blocks are correct or not. So if we do so, after elimination of this particular loop or this feedback path, the block will have, the representing block will have a transfer function 1 by R1 R2 C2S plus R1 plus R2. Please check. So now we are left with a single feedback path. The forward path gains are 1 by SC2 into 1 by R1 R2 C2S plus R1 plus R2. And the feedback path gain is R2 C2S plus 1. So this two, if you multiply this with this, then I'll get the forward path gain G, and this is our feedback path gain H. So the transfer function, the closed loop transfer function, where the input to the system is delta Q and the output from the system is delta Q2S, will be given by G by 1 plus GH, and please check whether this is the transfer function or not. These are the steps which I have already explained. The second topological model, graphical model or pictorial representation of a linear time invariant system is known as signal flow graph. In short, we call this SFG. SFG, the acronym is SFG, signal flow graph. So signal flow graph was actually proposed by S.G. Mason, and the advantage of signal flow graph, we'll discuss what is a signal flow graph. The advantage of signal flow graph is that if you can represent the system with the help of signal flow graph, that is a graph or a network, right? So if you can represent the system with the help of signal flow graph or signal flow network, then it was introduced by S.G. Mason. So Mason has provided us with a formula with the help of which we can simply apply Mason's gain formula for finding out the transfer function of the system represented with the help of signal flow graph. So we don't have to go for block diagram reduction technique, and for really complicated system, complex systems having a large number of interconnected loops, etc. The block diagram reduction technique is really very tedious, cumbersome, and time consuming. Whereas for signal flow graph, only what you'll have to do, you'll have to represent the system like a network, which will be a signal flow graph, and after that just apply Mason's gain formula and you will get the transfer function of the system. Directly you'll get the transfer function. Actually you'll get the gain between the output and the input of the system, and we know that that is basically the transfer function of the system. Okay. So that is the advantage. Very easily we can find out the transfer function of a complex system using this method. Now what is a signal flow graph? A signal flow graph is basically a graphical representation of the relationships between the variables of a set of linear algebraic equations. So let me show you a set of linear algebraic equations. So these are four algebraic equations which are related to each other, and the signals or variables. So when I'm talking about equations, I can use the term variables, and variables, when we talk about variables in the context of a system, then the variables are basically the signals at different points of the system. So here you see, we can see 5 variables: x1, x2, x3, x1, x2, x3, x4, x5. x2 is related to this x1, x3, x4, x5. x3 is related to x2, and x2 is basically linear combinations of x1, x3, x4, x5. Again, x4 is linear combination of x3 and x4, right? So given a set of linear algebraic equation, the relationship, the interdependence amongst the variables of the set of linear algebraic equations can be represented with the help of a network, with the help of a graph, and that is known as signal flow graph. Again, I repeat, a signal flow graph is a graphical representation of the relationships between the variables of a set of linear algebraic equations. Now, please do respond. Listen carefully. Now, our claim is that with the help of signal flow graph, we can represent the dynamic behavior of a linear system. But we know that the dynamic behavior of the linear system are actually represented with the help of integral differential equations. Right? Period. But here we are claiming that the signal flow graph actually represents the relationship of the variables of a set of linear algebraic equations, not a set of linear differential equations. Then with the help of signal flow graph, how can we model a linear system, linear dynamic system?
By using Laplace transformation.
Yes. So if we transform the domain from time domain to Laplace domain, the differential equations will become algebraic equation, a set of algebraic equation, and hence in the transform domain we can draw the signal flow graph and we can find out the construction of the system. So it consists of a network in which there will be some nodes, and nodes will be connected with the help of a branch. This is the branch, the straight line or this line. This curved line is basically a branch, and the small circles represent the nodes. Nodes are nothing but the system variables or signals associated with the system, right? And this directed branch, okay, I'll come to path. Okay, I'll give you the proper definition. Anyway, so it consists of a network in which nodes representing each of the system variables are connected by directed branches. Here you see E is connected to R with the help of this branch, and it's a directed branch. There is an arrow, and this arrow is very, very important because arrow directions shows the flow direction of the signal, in which direction the signal is flowing. From this node to this node, the signal is flowing from this node to this node. Okay, and these are the branch transmittance or branch gains. So when the signal flows from this node to this node, in the process the signal gets multiplied by this branch gain. Right? So this is the node E, C, which is connected to this node E, and the branch gain or branch transmittance is G. So C, the value of the signal will be simply equal to this into this. Signal will flow from this node to this node, and the process will get multiplied by this branch transmittance. Hence the value of the signal at this particular node C will be equal to E into G. Now look at this. This is a representative signal flow graph representing the closed loop configuration, where the forward path gain is G and the feedback path gain is H. So how many nodes will be requiring for representing such a system? Do I have to show the block diagram, or you'll be able to recall? R is the reference input, that signal. Then we'll get the actuating signal. Then we'll get the controlled output, that particular signal. Then B will the feedback signal. Can you recall?
Yes, ma'am.
Right? So at this point E, you see at this particular node, two signals are entering. One is h into -1, the other one is r into 1. So r minus h. We know the value of E is equal to, sorry, r minus b into h. Sorry, r minus bh. And we know from our knowledge of block diagram, we know that E is equal to r minus bh. Similarly, C will be, as I told you, G into E. E will be equal to C into H. Okay, so this is basically the representation of the closed loop, typical closed loop configuration of a system, a controlled system. And often this representation is modified, and why that is modified, we'll discuss that. Modified, and we actually represent the closed loop configuration with the help of this graph, this signal flow graph. Here we have added one more branch, having a branch gain 1. So hence, if the signal value at this point is C, that is the control output, the signal value at this point will also be C. C into 1, so this one will be C. As simple as that. Now let's go through some basic definitions. Node. Already we have introduced to this term node. So node, it represents a system variable which is equal to the sum of all incoming signals to the node. Remember, the signal value at a particular node will be equal to the sum of all incoming signals at that node. And also, please do remember that outgoing signals from the node do not affect the value of the node variable. So, from our knowledge, we can verify this or validate this particular definition, because we know that yes, the error signal, the signal value at this particular node will be sum of the incoming signals, sum of all the incoming signals. So this is r into 1. The value of E will be equal to r into 1 minus or plus b into h into -1. Right? Similarly, the value at this particular node will be
h into -1, man.
b into h into -1. This is the second
into h into -1, na, ma'am. B is the node, na. B is the node, so B is equal to CH and
CH
is equal to
sorry.
R minus B.
Yes, you are absolutely right. Yes. B is equal to C into H, either R minus B or R minus C into H. I'm extremely sorry. Now am I right?
Yes, ma'am.
Yes, ma'am.
So please do remember, outgoing signals from the node do not affect. This is one outgoing signal from this particular node, but it does not affect the signal value at this particular node. Next is branch. A signal travels along a branch from one node to another node in the direction of branch arrow. So always we'll have to move along the direction of branch arrow. We cannot move against the direction of the branch arrow. So the signal travels along a branch from one node to another in the direction indicated by branch arrow, and in the process gets multiplied by the gain or transmittance of the branch. For example, the signal reaching the node C from the node E is given by G into E, where G is the branch transmittance. So while you'll be developing the signal flow graph, or you'll be sketching the signal flow graph, please do remember that the branch gain, it could be 1, but you'll have to write down the branch gain and you'll have to put arrow in the appropriate direction. Otherwise, if the branch transmittances are not known, and if the direction of flow of signals are not known, then you will not be able to find out the transfer function of the system. You won't be able to apply Mason's gain formula. Am I clear? So be very, very careful to put branch arrows and to write down branch transmittances like this as is written over here. Okay. And if the branch transmittance is 1, you cannot ignore it, or you cannot assume that it will be considered by default. You'll have to write down the branch transmittances which are unity. 1, 1, like this. Next is input node or source. It is a node with only outgoing branches. So look at the signal flow graph. So from this we can see, we can identify one single node which has only outgoing branches. For this node, if I consider this node, one outgoing branch, one incoming branch. Okay. That is valid for this one also. So in the signal flow graph, R is the input node or the source. Similarly, output node or sink, it is a node with only incoming branches. Source only outgoing branches, sink only incoming branches. However, this condition is not always met, or in a signal flow graph often it's difficult to identify an output node. So if I consider this only incoming branches, so we know that this is the output variable. From our previous knowledge, we know that this is the output variable. Why output node and input node? Why we need to identify output node and input node? To identify which one is the input signal and which one is the output signal, right? That's why. So in this signal flow graph, there's a correct signal flow graph, but the problem is it's difficult to identify the output node, because you see for this node there is one incoming signal, one incoming branch, the other one is the outgoing branch. That's the reason we introduce another branch like this. We add an additional branch having a branch gain 1, right? And so if we just modify the signal flow graph in this form, then you see this node can be easily identified as the output node, as it has got only incoming branch, one single incoming branch. Am I clear? So if you look at the signal flow graph, it will be clear to you that this one is the input signal and this one is the output signal. And you'll have to obtain the transfer function, you'll have to find out the gain C by R. So however, this condition is not always found. An additional branch with unity gain may be introduced in order to meet the specified condition. Now next one is path. What is a path? It is the traversal of connected branches in the direction of branch arrows, such that, this is very important, this condition is very important, such that no node is traversed more than once. No node is traversed more than once. So it is the traversal of connected branches. So let's get back to this signal flow graph. So this is one path, R to E to C to C, right? We are moving from this node to this node. We are moving along the connected branches, along the branch arrow, along the direction of branch arrow, right? But if I start from this particular node and move to this node, and then try to move to this node and try to define this to be a path, that is not a valid path. Why? Because I'm moving against the direction of signal flow, which is not allowed, right? So this one will not be a path. Here, so this one is a path, this one is a path, or you can define this one to be a path. Forward path, it is a path from the input node to the output node. Actually, forward path will give us the forward path gain. So in the signal flow graph, this is our forward path. This is our forward path, which is connecting the output node to the input node. This is not a forward path, and it's not connecting, this path is not connecting the output node to the input node. Loop. Loop is a path, but a special kind of a path. It is a path which originates and terminates at the same node. Originates and terminates at the same node. Okay. And since loop is a path, hence this condition has to be satisfied. That is, no node is traversed more than once. So if I start from this node, if I move like this, and then if I move like this in the direction of branch arrow, and we start moving along this, then this cannot be considered to be a path. Why? Because we are traversing this node twice, which is not permitted. And what is a loop? A loop is a path which is originating and terminating at the same node, but in the process we are not traversing any node twice. So in this diagram, in this signal flow graph, in this graph, this is a loop, E, C, B, and then E. So the loop is a path. You see, I'm moving along the direction of branch arrows. So I'm starting from this particular node. This is the originating node, and I'm terminating at this particular node only. I'm not traversing this node again. Just I'm originating, the loop is originating from this particular node and terminating at this particular node. So that's why it's a called loop. And in case of loop also, don't get confused, we are not traversing this node twice, right? And in this case, there's a path. In this case, you see, we are originating from this particular node and we are terminating at this particular node. So that's why this is not a loop. Non-touching loops. Loops are said to be non-touching if they do not possess any common node. So in a signal flow graph, you can have multiple loops, right? So if two loops do have a common node, then those two loops will be called to be touching loops. But if we find two loops in the graph such that the loops do not have any common node, then the loops will be called to be non-touching loop. Or non-touching loops, sorry. Non-touching loops. Now forward path gain. Forward path gain is the product of branch gains encountered traversing a forward path. For example, the forward path gain of REC. REC will be 1, or let's consider this graph. So the forward path gain or this path gain will be 1 into G into 1. That is G. Forward path gain, it is the product of the branch gains encountered traversing a forward path, and loop gain, same as path gain, it is the product of the branch gains encountered traversing the loop. So this is the loop in this a single only loop present in this graph. So the loop gain will be G into H into minus 1, that is minus GH. This is the loop gain. Okay. Construction. Construction of signal flow graph and Mason's gain formula that I'll discuss in the next class. So what we have discussed in this class, do you have any question? Do you have any question?
Well,
আচ্ছা, কনস্ট্রাকশন অ্যান্ড মেসনস গেইন ফর্মুলা ওয়েডনেসডেতে তোমরা ক্লাস করবে না আমি রেকর্ডিং পাঠিয়ে দেবো? 27 জন তো, 27 জনও নয়, এখন কজন আছো? দেখতেও পাচ্ছি 27 জন আছো বোধহয়, নাকি? কি করবে বলো, তাড়াতাড়ি বলো। হ্যালো, মাইক্রোফোন অন করো প্লিজ।
অ্যাকচুয়ালি সেই মানে অনেকে করছে না।
কিন্তু কেন করছে না? তোমাদের তো 27 তারিখ অবধি তো তোমাদের সেশন আছেই। তো তোমরা যে কজন আছো তোমরা কি করবে না? আগের দিন 40 ছিল, আজকে 27 হলো, নেক্সট দিন 12 জন হয়ে যাবে। আচ্ছা, আজকে আমি তোমাদের সব ম্যাটেরিয়াল পাঠিয়ে দিয়েছি, পেয়েছো?
ইয়েস ম্যাম, ইয়েস ম্যাম।
ঠিক আছে, বুধবার আমি একটা স্লট দিয়ে দেবো, 6:30 থেকে স্লট দিয়ে দেবো, যে কজন আসবে সিগন্যাল ফ্লো গ্রাফ আর মানে যেটুকুন বাকি আছে সেটুকুন ডিসকাস করে দেবো। যত একটু ইয়ে করে দাও তো আমাকে।
হ্যাঁ ম্যাম, একটু ওয়েট করুন।
যারা আছো একটু ইন্টারঅ্যাক্ট করো তো প্লিজ, এক এক করে, একসাথে সবাই আনমিউট করো না। যে কজন আছো তোমাদের সবার ভ্যাকসিনেশনের 2টো ডোজ কমপ্লিট হয়েছে?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
আচ্ছা, এবার ইউনিভার্সিটি খুললে তোমরা কি ফিজিক্যাল মোডে ক্লাস করতে আসবে? মানে যখন তোমাদের অ্যালাউ করা হবে আর কি।
ইয়েস ম্যাম।
কি করে আসবে?
আমি
তো তোমরা তো বাড়িতে বসে ল্যাপটপ অন করেই তো ক্লাস করো না
ম্যাম ট্রেন বা মেট্রোতে।
আমার কথাটা শোনো তার মানে তো বাড়িতে সকাল সকাল উঠতে হবে, উঠে রেডি হতে হবে, রেডি হয়ে কমিউট করতে হবে, বি ট্রেন অর মেট্রো অর বাস বা হেঁটে সাইকেল হোয়াটএভার, কমিউট করতে হবে, টাইমে কলেজে আসতে হবে, তাই তো? অনেক পরিশ্রম না? অনেক বেশি পরিশ্রম না? বাড়িতে বসে ল্যাপটপটা অন করে ক্লাসটা শোনার থেকে সেইটা তো অনেক বেশি পরিশ্রম, হ্যাঁ না? আরে ইন্টারঅ্যাক্ট তো করো।
হ্যাঁ ম্যাম,
বাড়িতে তো যেরকম ভাবে আছো সেইভাবে কোনো রকম একটু কষ্ট করে ল্যাপটপটা অন করতে হবে, লিঙ্কটাতে একটু ক্লিক করতে হবে, কানে একটা ইয়ার প্লাগ দিতে হবে, আর একটু মন দিয়ে ক্লাসটা করতে হবে। এই তো, তাও মন দিয়ে ক্লাস করছো কিনা সে তো আমি আর এখান থেকে প্রক্টরিংও করতে পারছি না, তো ফিজিক্যাল ক্লাস নয় যে তোমাদের চোখ মুখ দেখে বুঝতে পারবো কে কতটা বুঝেছো বা কিছু, সেই ফিডব্যাকটা তো আমার কাছে আসছে না। তো যাই হোক, এইটুকুন করতে হবে। ফিজিক্যাল মোডে ক্লাস করতে গেলে তার মধ্যে 1.5 বছরের অনভ্যেস, রেডি টেডি হয়ে খেয়ে দিয়ে তারপরে টিফিন, জলের বোতল, এখন তো স্যানিটাইজার, মাস্ক, কত সব জিনিসপত্র আছে, এইসব নিয়ে টিয়ে ট্রেনে করে এসে ক্লাস করতে হবে। কি করে করবে? সেটাই তো আমি বুঝতে পারছি না। বাড়িতে বসে ক্লাস করতে এত আলস্য, এবং এই 27 জন ছাড়া বাকি সবার নেটওয়ার্ক ইস্যু, এইটা বললে কিন্তু আমি মানতে রাজি নই, তাই না? দুটো সেকশন মিলিয়ে আমি 70 জনের বেশি আছে তোমাদের একটা সেকশনে, সো 140 যদি ধরি, সেইখানে 27 জনের কোনো নেটওয়ার্ক ইস্যু নেই আর বাকি সবার নেটওয়ার্ক ইস্যু, এটা তো হতে পারে না। যা করবে, যারা ক্লাস করছো না তারা পরে বুঝবে। ওকে, আই এম এন্ডিং দিস সেশন।